Hello everyone, let's talk about normalizing relations. At the end of this series of videos, you will be able to convert an unnormalized relation into 3NF, or third normal form. And that involves breaking it up into multiple relations and preserving all the functional dependencies in the process. Remember when we used to think that a table was the same as a relation? We generalized those two terms. We're not doing that anymore. We're going to differentiate between the two. A relation will be something created in the logical design step of the database, and a table will be the entity that you see in SSMS when you open up SQL Server. We still call it an RDBMS, a relational database management system, but when we create a table in our RDBMS, it does not have to be normalized, and it is not strictly a relation, even though the term relation still appears in the generic description of that tool, RDBMS. Remember your terminology. We've talked about these keys. We are primarily interested in the candidate key as we go through this process. We're going to drop the concept of a primary key entirely while we discuss normalization. It doesn't matter what the primary key is. It only matters that there are one or more candidate keys. We're going to drop the concept of a surrogate key completely because that doesn't come into existence until the logical design phase is completed and we begin the physical implementation. We're dropping surrogate. We're dropping primary, and foreign key is a convenience that we don't necessarily need, but we may talk about it. Natural, all of our keys will be natural because they're all going to come from the problem domain since we dropped surrogate. And we may end up creating a candidate key that is composite. New terms. The columns in a table will be referred to as attributes. And remember, we're talking about a process where we don't even have a table yet. That's why the terminology differs a little bit. If an attribute appears in one or more candidate keys, it's called prime. If an attribute does not appear in any candidate keys, it's non-prime or non-key. I typically say non-prime. This means that every attribute in every relation is either prime or non-prime. It cannot be both. It cannot be neither. It has to be one or the other. We'll also say that every relation has at least one candidate key. And since we're only talking about keys in the problem domain, that will be a natural key. We're not going to worry ourselves with a set of data that cannot be uniquely identified by row. The reason we normalize is that it reduces the possibility of creating inconsistent data because it reduces the possibility of deleting things that we might want to keep and updating things that we might not want to update. And we refer to that as update and delete anomalies. So if you're asked on the street or at the next Super Bowl party why we normalize, it is to avoid update and delete anomalies. And some people also add insert anomalies to that too. In terms of performance, normalization is great for updating transactions, insert, delete, and modify rows in the tables. Updating is a hindrance, normalization is a hindrance for retrieving data from tables because everything is spread out over multiple tables and that takes time to connect all those tables using join statements in your SQL. For our purposes, doesn't affect us in the least because we don't have a lot of data, but if you have a concern, if you're scaling up and you have huge volumes of data that take significantly large amounts of time to retrieve, then you need a different physical model. The term that we use for a database that's optimized for retrieval is data warehouse, where we are storing duplicate values intentionally, and we are not normalizing in the same style that we talk about here. We've got a lot of calculated fields, and that lets us retrieve the data much quicker than redoing all those calculations on demand. Well, that's not a topic for us, but I just want to give you some context that data warehouses are another field of study in data science, and we're not talking about that beyond these two slides. A couple very important things. We don't normalize data. We don't normalize data. We normalize the logical design, which is a relation. And sometimes I will refer to that relation as a schema, but that is not strictly correct. Actually, I'm going to change that right now. So when you see this slide, you will not see the word schema there. Don't use your intuition. Don't look at the data. Don't decide that based on a little snapshot that you have a normalized table. It's too late at that point. The design work happens at the logical step, and before that, even at the conceptual step. You have to know something about the semantics of the problem you're solving to define the requirements for normalization, the determinants. So we need a domain expert to do this. The domain expert is going to help us determine what the functional dependencies are and also what the candidate keys are. Just a narrow point, but it is just all over the internet. Never say this table is normalized. Be specific. There are many levels of normalization, as you read about in the book. We're only going up to 3NF, but when you say that a relation is normalized, you actually shouldn't say table either. I'm going to make a couple of corrections as I go along here. This relation is normalized. Well, let's not do that, because once you get to that point in the physical implementation, then you've already proved that you've done it in a logical step. So we'll go ahead and we'll live with that. But do not say that a table is normalized. Say that the table is normalized to a particular level. I'm just giving you some critical thinking tools here. And if we were standing in line at Gold Star waiting for our burritos, I wouldn't correct you if you said a table is normalized, but I would prefer that you be a little more specific. The concept of a functional dependency is crucial. A and B are attributes in a relation. They don't have to be prime. They don't have to be non-prime. A dependency, an FD, can exist between a prime and a non-prime, a prime and a prime, a non-prime and a non-prime. Any combination of two attributes can participate in a functional dependency. And knowing whether or not the attributes are prime or non-prime goes toward the normalization process. Now we are going to say, for our purposes, these FDs come from the problem domain. They are semantically defined. They are a derivative of the problem we're trying to solve. And that means that we don't get to make these up. Somebody gave them to us. You have to know something about the problem you're solving. So the systems analyst, in conjunction with the customer, would work together to define these. If you're a DBA and you're given a table, I'm sorry, even I do it, you're given a relation, you should also be given the functional dependencies along with that relation. They are not up to you to derive. And I've got a couple examples at the end of one of these slideshows that just illustrate what I consider to be incomplete or improper explanations of these topics all over the internet. Here's what I just said. I'll emphasize it again. Determinants come from the problem domain for our purposes. we're trying to solve real world problems. We're not mathematicians. So you may see a strictly mathematical explanation of these topics where the determinants are just poofed out into existence, but they come from somewhere or they don't have any value to us. We cannot create or destroy determinants and functional dependencies during the design phases. We have to preserve them all the way through. So if you're going through a normalization process and you find yourself creating a dependency, then you're doing it wrong. There's an example from the problem domain. We are told that at UC, a class determines a teacher. We met with the customer and they taught us that. We don't disagree with it or agree with it, we just accept it. Well, because of that, we can say there's a functional dependency between a class attribute and a teacher attribute. I gave an example here. The course Spring 2022 Band of 4143 Section 001 determines the teacher. Now if you flip it around, it doesn't go the other way. If I give you the teacher, you cannot give me the course because a teacher could teach multiple courses. Here's an example of one that does go in both directions. If I give you an M number, you can give me that person's social security number. And if I give you their social security number, you can give me their M number. Now I'm assuming here that everybody has a social security number in this UC database. I mean, there's many underlying assumptions going on here. If I'm incorrect, fine, but that is my assumption. Let's look at a larger scale example. I contrive these examples very carefully so that they're narrow. They are not meant to reflect things in the real world because if they were, they would go on for 20 pages and just become overwhelming. Therefore, don't fight with me about my semantics because they are intended to keep us between our lanes and to get us to the end point as quickly as possible. An XYZ company makes boats. Every boat has a unique serial number. Okay, you can kind of see that coming down as it's going to be some kind of key. A customer purchases one or more boats, fine, but never more than one boat in a day. Well, you can see right away that's not something any customer would want, because if I gave them a database solution and I told them they couldn't sell 2 boats to the customer in the same day, they would laugh me out of the showroom. But it works for us. Each boat is sold by one sales rep. Again, that's pretty limiting. Sometimes sales reps split commissions, especially on more expensive items. A sales rep may sell multiple boats in a day. That's reasonable. No boat is ever sold more than once. Yeah, that's rough. You can't take a boat in trade and sell it again. And again, this is just to keep us in a very limited scenario to make solutions easy. Based on the previous semantics, we can create a logical design. This would be a relation. So I'm careful not to say table, and I do once in a while accidentally, but I'm careful not to. We have underlined attributes. The syntax here is that if it's underlined, it's a candidate key. Boat serial number is underlined, and that means the boat serial number is a candidate key in this relation. And then another candidate key is customer and date of sale together, so that's a composite candidate key. This relation has 2 candidate keys. I don't care about primaries yet. Primary key is an indication of how the data is physically organized in the RDBMS, not an indication of how it's normalized. So we don't care which one is primary. Also notice there's no surrogate at this point. Surrogate keys aren't going to come into play until the physical step. And then I create as many functional dependencies as I can based on the semantics on the previous slide. So if I know the boat number, if I know the boat serial number, I know the boat type, If I know the boat serial number, I know the manufacturer. If I know the boat serial number, I know the price. Then if you backtrack all of these, most of them come directly from the previous slide. A couple I just made up. But boat serial number and price means that if I know the boat serial number, I know the price. That means I only sold the boat once, because if I sold it twice, I wouldn't be able to tell you what the price was on that boat. Boat serial number tells me customer. Again, whoops. If I sold it more than once, that wouldn't apply. But since I have the stipulation I can only sell a boat once, then I can tell you who the customer is. Boat serial number determines date of sale. Since I can only sell it once, I can tell you the date I sold it. Boat serial number determines sales rep. If I only sold it once and only one sales rep can sell a boat, then I know who the sales rep is. Same thing for the candidate keys. If I know who the customer is and I know when they came in, I can tell you what boat they bought. If I know the customer when they came in, I can tell you what kind of boat it was. If I know the customer and the date, I can tell you that what kind of or who made the boat. If I know the customer and the date, I can tell you what they paid for it, and so on. That's our overview of functional dependencies and normalization, and we will continue on to the next video. Thank you.